Hello everyone. This is part 4 video on past year NEET questions in physics from the chapter thermodynamics. Those who are looking at this video can also take a look at the previous 3 parts so that you will not miss out on the relevant models of questions. We'll start with a question that has come in the mains paper 2011. So previously AAPMT, All India Pre-Medical Test, there used to be that mains, prelims and mains kind of a format. A mass of diatomic gas. So for the diatomic gas, gamma will be what? 7/4, or in terms of decimal number, it is what? 1.4. Okay, so mass of a diatomic gas at a pressure 2 atmospheres is compressed adiabatically so that its temperature is rising from where to where? 27 to 927. The pressure of the gas in the final state. It's a straightforward kind of a question where we have to look at the relation between the pressure and temperature of the gas in the adiabatic process. So we know the parameters of the gas, right? Pressure and volume are related by what? PV power gamma will be constant. Temperature and volume also related. PV power gamma minus 1 will be constant. Temperature and pressure related. P power 1 minus gamma into T power gamma will be constant. Otherwise, this can also be written as T power gamma divided by P power gamma minus 1. So either we'll have P power 1 minus gamma in the numerator, or we'll have P power gamma minus 1 in the denominator. Okay, because when you move a term from numerator to denominator, the power overall will become what? Negative. So multiply the 1 minus gamma with minus, we'll get what? Gamma minus will come. That will be the power of P when it goes to the denominator. Either we use this one or we use this. So T power gamma into P power gamma minus 1 will be what? Constant. Now here the initial pressure is given, initial temperature is given, but no, we have to keep in mind initial temperature 27 means what? We should take the temperature in Kelvin scale. It will be what? 300 Kelvin. Final temperature is 927, means in Kelvin scale we have to add what? Plus 273, right? It will become what? 927 plus 273, it will become 1200 Kelvin. Okay, pressure can be in any unit, whatever. So what is the unit for the final pressure going to be? Since the initial pressure is in ATM, final pressure also will be in the ATM only. So if you look at it, right, T initial power gamma divided by P initial power gamma minus 1 is equal to T final power gamma divided by P final power gamma minus 1. So here we are looking for what? The P final. So what we'll do is we'll just bring the pressure term to one side. So bring the pressure this side, take the temperature that side. So what we'll have from here? P final by P initial, both will have the same power. Power gamma minus 1 is equal to what? T final by T initial power gamma. Both the terms on RHS also have the same power. T final by T initial power gamma. Now we are looking for P final value, right? Let us do away with the power. So what is the power here? Gamma minus 1. We'll take a root of gamma minus 1 on both sides. Root of gamma minus 1 means what? On both sides we will be raising the power to what? So already there is a gamma minus 1 power. On both sides we will raise the power to what? 1 by gamma minus 1. So T final by T initial, already there is the power gamma. We will raise it to what? 1 by gamma minus 1, both sides. Then here this gamma minus 1 is cancelled. What we will be having? We will be having P final by P initial is equal to what? RHS side, T final by T initial whole power gamma by gamma minus 1. So P final is required. So P final will be what? P initial into T final by T initial whole power gamma by gamma minus 1. So this simplification, right, in terms of getting the P final value is something that we need to little bit practice so that we will not make any mistake while adjusting the powers and all that. Okay, so it's just rearranging them and trying to express the P final in terms of the other variables, because here we are looking for what? Just the P final value, right? Powers are not needed here. We should be getting what is the P final value. And by the way we see these options, right, we get a feeling that okay, there might be some easy simplification that could be happening. The powers and all might get easily simplified. So we need not have to do much work while simplifying these powers. That is what is the understanding we will get when we look at these options. So that's the reason why, when you're solving the questions, right, you should just keep an eye on the option so that you will get a feeler. Okay, so this problem we could be having the powers getting simplified easily. So let me write down the final expression for the P final. P final is equal to what? P initial into T final by T initial whole power gamma by gamma minus 1. Now I have seen some students, if you remember that previous three expressions, right, what are the three expressions that we have for the adiabatic process? P into V power gamma is constant, T into V power gamma minus 1 is constant, P power 1 minus gamma into T power gamma is constant. These are the three expressions we have seen, right? Some people also try to remember these kind of derived results. Now my advice will be that, okay, don't try and do that much of memory exercise, because it might just collapse everything. Think about it, right? Even if instead of plus we put a minus, what is going to happen? The entire problem will be going for a toss. So you try to remember those three base relations, and whichever problem is given, right, we can just quickly derive like this. So what is the final formula we have? P final is equal to what? P initial into T final by T initial whole power gamma by gamma minus 1. So this is the expression we have. Now in this, what is the given data? P initial is given as what? 27, means we said already temperatures must be on the Kelvin scale, 300. T final is what? 927, means 1200. P initial is what? 2, and gamma is 1.4. Okay, diatomic gas means what? Gamma is 1.4 or 7/5. That itself they have given. Sometimes, even if they are not giving, we should be able to remember. For the monatomic, what is the gamma value? 5/3. Diatomic 7/5. These two values we should remember importantly. Now what is it? Just go and substitute. P final is equal to what? P initial is 2 into T final is what? 1200 by 300. Gamma is 1.4 by gamma minus 1. So you see here, what is it? 304s are 1200. Okay. So what we'll be having is 2 into 4 power 1.4. What is the denominator? 1.4 minus 1 means what it is? 0.4. So if you see, right, this 1.4 by 0.4, we can write as what? 1.4 by 0.4 means just multiply both by 10. We'll get 14 by 4. Means what? 2 2s are 2 7s are. That will be what? 7 by 2. So what we'll have is this 1.4 by 0.4 can be written as what? 7 by 2. And the 4 can be written as what? 2 square. So you see, 2 square whole power 7 by 2. So the 2 will get cancelled in the power. What we have? We'll just be having 2 into 2 power 7. What is 2 into 2 power 7 means 2 power 8. 2 power 8 will be 256. So the answer is option D. The final pressure will be what? It will be 256 atm. Okay. So we have seen that quite a number of years we got this relation between the parameters of the gas with regard to the adiabatic process. Next we have a theoretical question. This has come in the 2010 paper. If delta U and delta W represent the increase in the internal energy and work done by the system respectively in a thermodynamical process, which of them is true? See, they are giving 4 options. In each option they are talking about some situation. So this question, right, we have to go through the options, then only we can conclude which of them is actually true. Look at option A first. Delta U is equal to minus delta W in adiabatic process. Adiabatic process means what? The del Q will be 0. What is the first law? Always, so these relations are given by what? The first law of thermodynamics, right? What is the first law of thermodynamics? Del Q minus delta W is equal to what? Delta U. So whatever the heat that is absorbed minus work done will be equal to what? The increase in the internal energy, delta U. Okay. So if delta U positive means we will say increase, delta U coming negative means it will be what? Decrease. Okay. It depends upon the sign. Now look at it. We are saying what? Adiabatic means del Q is 0, right? So what is the relation we have? Delta U is equal to minus delta W. Straight away we are able to get the answer. So option A is the correct one. Look at option B. Option B is saying what? So we'll also check the other ones. Option B is saying delta U is equal to delta W in isothermal process. Isothermal process means what? Delta U is actually 0 because temperature remains constant. If you take an ideal gas, right, delta U is equal to what? NCV delta T, right? What is the delta U? Change in the internal energy is what? N into CV into delta T. So which means if the temperature is remaining same, that is what happens in the isothermal. Delta U will be 0. So here this is not correct. Look at option C. It's saying delta U is equal to delta W in adiabatic process. So just the sign difference is coming. So adiabatic, if no heat is supplied to the system, look at this. The significance of this delta U is equal to minus delta W means what? If the delta W is negative, then delta U will be positive. Means what? If work is done on the system, that is when the delta W will be negative, right? That work is done on the system. Then as a result of it, the internal energy will be what? Positive. If delta W is positive, means work is done by the system. Then you see delta U will be what? Negative, means work is done at the expense of the internal energy. By losing internal energy, the system is doing work because no heat is coming from outside. That is what is the significance of this negative relation. Okay, so this is not correct. Option D is what? Del U is equal to minus del W in isothermal. Again same thing. Isothermal means what? Del U is actually 0. Next we have a question that has come in the mains paper 2010. If Cp and Cv, these are small symbols you can see, denote the specific heats per unit mass of an ideal gas of molecular weight M, then so if you look at the options, they are expecting us to tell what is the relation between these Cp Cv values and the gas constant R as well as the molar mass. See, what we know is the molar specific heats. So let us represent them by the capital symbols. Molar specific heats, right? They have a relation. What is the relation? Capital Cp minus capital Cv will be equal to what? R. This is the relation between the molar specific heats. Now here they are not giving the molar specific heats, they are giving what? Specific heats per unit mass. See, let us understand. Take for example oxygen. What is the molar mass of oxygen? 32 grams. We're taking the oxygen gas, okay. Now what does capital Cp represent? It represents what is the heat required per unit temperature change per mole, because they are the molar. Okay, similarly Cv will be what? Heat required per unit temperature change per mole. So this will be at constant pressure, Cv will be at the constant volume. Okay, now if you look at it, per mole means per 32 grams of oxygen. So this is the heat required per unit temperature change for 32 grams of oxygen. What will be the heat required for unit temperature change for 1 gram of oxygen? That is what you are calling as the small Cp. So small Cp will be equal to what? Capital Cp divided by the molar mass. Because say for example for 32 grams, it is requiring some amount of heat per unit temperature change, that is capital Cp. We have to divide that by the molar mass. We have to divide that by the 32 grams in the case of oxygen. That is what is going to give us per gram how much heat will be required per unit temperature change. So similarly small Cv, right? What will be the small Cv value? It will be capital Cv divided by the molar mass. This is an important relation, and this is also a very standard question. Why? Because this question can be asked by changing the numericals. Even in future NEET examination, by just changing numericals, in the sense they can specifically ask for a particular type of gas, like for nitrogen, what is the relation? Like that we can expect some questions. So what is the relation between specific heat per unit mass and specific heat per mole? The small Cp will be equal to what? Capital Cp divided by molar mass. Similarly small Cv will be equal to what? Capital Cp divided by molar mass. Already we have a relation. The relation is what? So here what we can see here is that the capital Cp will be what? Molar mass into small Cp. Similarly capital Cv will be what? Molar mass into small Cv. Already we have a relation between capital Cp and capital Cv. That is Cp minus Cv is equal to R. So some of us should not just confuse the relation with option B, because option B is saying what? Small Cp minus small Cv is equal to R. This is not correct. Capital Cp minus capital Cv will be equal to R. The relation is in terms of the molar specific heats. Now we'll just substitute in place of capital Cp. What is it? Molar mass into small Cp. Here also molar mass into small Cv, that is equal to what? R. Okay, so what we'll have is if you take out the m common, small Cp minus small Cv is equal to R. So from here what we'll get? The Cp minus Cv will be equal to what? We'll just take the m to the other side. It will go to the denominator. It will be equal to what? R by m. So what is the correct answer for this? It is option C. Like I said, how they can give possibly questions in future. They can say for nitrogen gas. For nitrogen gas means what? N2, right? What is the molar mass of N2? 28 grams. So in that case, what will be the relation? Small Cp minus small Cv is equal to what? R by 28. Like that we'll get the relation. For oxygen means it will be what? R by 32. So depending upon the gas, right, the molar mass will essentially change. So it's a standard relation. We can have specific problems asked by just giving what is the particular type of gas. In that we have to use the respective notation. Okay. So this is about the relation between small Cp and small Cv. Of course here, right, we have to be careful about the units. We have to be careful about the units. So if you look at the R will be generally in what? SI units, and the molar mass, if it is in grams, we should be converting into what? Kilograms, provided we are trying to have everything in the SI system of units. So we have to be careful about the units part, but the basic relation is this: Cp minus Cv is equal to R by capital M. All the things should be in the same system of units. Okay, we'll go to the next question. This is a question that has come in the mains paper 2010. A monoatomic gas at pressure P1 and volume V1 is compressed adiabatically to 1/8 of the original volume. So here the gas is what? Monoatomic. Monoatomic means gamma will be what? 5/3. Initially what is it? Pressure P1, volume V1. It is compressed adiabatically to 1/8 of the original volume. Means final volume V2 will be what? V1 by 8. We have to find what is the pressure P2. So in an adiabatic process we have a relation, right? What is it? P into V to the power of gamma will be what? Constant. Means P2 V2 power gamma will be P1 V1 power gamma. So P2 will be equal to what? P1 into V1 power gamma by V2 power gamma. So that is what? P1 into V1 by V2 whole power gamma. So P2 is equal to what? P1 into V1 divided by V2 is what? V1 by 8. Okay, gamma is what? 5/3. So you see V1 V1 is cancelled, the 8 will go to the numerator. So what is it? P1 into 8 to the power 5/3. See here we'll have to do a simplification with regard to the powers. 8 can be written as what? 2 power 3, 2 cube, whole power 5/3. So here you see there is a cancellation. 2 cube whole power 5/3 means 3 will be cancelled. What is it? P1 into 2 power 5. 2 power 5 is what? 32, right? So it is what? 32 times P1. So the final pressure P2 is what? 32 times P1. So correct answer is option D. So we have seen quite a number of years we got the questions based on the adiabatic process, the relation between the properties of the gas. Next we have a straightforward question based on the first law of thermodynamics. The internal energy change in a system that has absorbed 2 kilocalories of heat. How much? The delta Q is what? 2 kilocalories means 2 into 10 power 3 calories, and done 500 joules of work. So W will be equal to what? 500 joules. Here if you see the work done is in SI unit, and heat absorbed is in calories. If you look at what they're asking internal energy change, means they're asking delta U. Options are also given in joules, right? Means we should convert this delta Q into joules. How do you do it? 2 into 10 power 3 calorie, 4.2 joules. So if we use it, right, what is it going to be? It will be 8.4 into 10 power 3 joules, means it is what? 8,400 joules. That is our delta Q. W is here. What is the first law? Del Q minus W is equal to delta U. So whatever the heat absorbed minus work done is equal to what? Change in the internal energy. Means what? 8400 minus 500. That is what? 7900 joules. It's a straight question. What is the answer for this? Option C is the answer. If instead of taking calories 4.2 joules, if you are taking more specifically 4.186 joules, like that, particularly if you are going with that number, you will have to choose the approximate answer. Okay, so we'll move on to the next question. This is a question that has come in 2009 paper. It's a theoretical question. In a thermodynamic process, which of the following statements is not true? Means we have to look at what is the incorrect statement. Okay, so these kind of questions, right, we have to go through each and every option, then only we will be able to answer. Option A, look at it. In an isochoric process, pressure remains constant. No, right? What is isochoric process means? Volume will be remaining constant, and also since volume remaining constant, work done will be zero. That is what is isochoric process. So the first one, because we are looking for which of the statements is not true. Not true means what? That is the one, right? So we got our answer. What is it? Option A is the answer. But we'll anyway look at the other options also. In an isothermal process, the temperature remains constant. That is it, right? Temperature remains constant, and for an ideal gas means delta U will be what? Zero. C is what? In an adiabatic process, PV power gamma is constant. We have seen, like in other problems also, these relations. PV power gamma will be constant. Then T into V power gamma minus 1 will be constant. P power 1 minus gamma into T power gamma will be constant. All these relations are very, very important, because we have seen quite a lot of questions coming on this. So that is also correct. We are anyway got our answer, but we are just trying to check if all the other options are correct or not. Option D is what? In an adiabatic process, the system is insulated from the surrounding. That is it, right? So we have a system. So what is the assumption? We will say we are covering the system with an adiabatic wall which will insulate it. That is the reason why delta Q will be what? Zero. So that is also correct. So what is the not true statement or incorrect statement? Option A, which we already got it. Okay. We'll move on to the next question. This is another theoretical question based on the cyclic process. This is coming 2008. If Q, E, W denote respectively the heat added, change in the internal energy, and the work done in a closed cyclic process. So what are they talking about? They are saying it is a cyclic process. Cyclic process, what is the basic thing about the cyclic process? You will start from a point, you will go through a path. I mean, it need not be just what I am writing here, it can be any path. So you will go through a path typically. So starting from A, you go to B, then you go to C, then you go to D, and then you will come back to A, like that. So whatever is your initial state, same will be the final state. That is what we call as cyclic process. If you look at the representation of the cyclic process on a PV diagram, right, how it is going to be? It is going to be like a closed loop. So you will go in a path. I mean, whether you have a anti-clockwise cyclic path or clockwise cyclic path, in both the cases, starting point will be ending point. Okay. So then which of these relations are true? That is what they are saying. See here clearly, since starting point is the ending point, the change in internal energy, here it is represented by what? The symbol E. Now you might be wondering, why are we not putting deltas? Because generally what do we say? Delta E or delta U, right? That represents the change in the internal energy. But since they are saying that, okay, just take E as the change in the internal energy, we'll just take it. So E is what? Change in the internal energy. And since the final point and initial point are same, what will be the change? Because internal energy is what? It is a state function. It depends upon the state. So E value will be equal to what? 0. So what is the correct answer for this? Option A. W will be what? It will be the area enclosed by the curve. Okay, so whatever the cyclic curve that is there, area enclosed. So we'll see that there is an area enclosed by the curve, right? So that will be representing the W. So it may be 0, it may not be 0. We cannot say. Q of course depends upon W. So we will not be able to say that W is 0 and Q is 0, because it depends upon the type of process. But what we can definitely say for any cyclic process is the change in the internal energy will be 0. So what is the correct answer for this? Option A is the right answer. Next we have a question on the heat engines. An engine has an efficiency 1 by 6. What is the efficiency of the heat engine? 1 by 6. When the temperature of the sink is reduced by 62, so here we're reducing the temperature of the sink by how much? 62 degrees Celsius. Its efficiency is doubled. Using this data, we have to find what is the temperature of the source. So here they are expecting that we use efficiency relation to temperature. Now remember, this can be only done if you are assuming that the heat engine is what? Carnot's engine. Because only for the Carnot's engine, eta will be equal to what? 1 minus T2 by T1, where T2 is the sink temperature in Kelvin and T1 is the source temperature in Kelvin. Okay. So initially, what is the relation? Efficiency is 1 by 6. So here we are going with the assumption that the heat engine given to us is what? Carnot's engine. Okay. Otherwise, we will not be able to relate the efficiency to the temperatures of the source and sink. Only in the Carnot's engine we can relate. This point we have to be clear. Okay. Now, initial case, what is the eta? 1 by 6 means 1 by 6 is equal to 1 minus T2 by T1. Okay, so we'll just bring the 1 to the left side. It will be what? 1 by 6 minus 1 is equal to minus T2 by T1. This means what? What is 1 by 6 minus 1? It is minus 5 by 6 is equal to minus T2 by T1. Minus minus is cancelled. Cross multiply, we'll get what? 5 T1 is equal to 6 T2. Let us keep it. So what is the first equation we are getting? 5 T1 is equal to what? 6 T2. So here what is the T1? The high temperature, which is the source. That is what we are trying to find here. T2 is what? Sink temperature initially. Okay. Now what are we doing in the second situation? The temperature of the sink is reduced by 62 Celsius. Now remember one thing, the change in temperature on Celsius scale will be same as change in temperature on the Kelvin scale. So if you reduce the temperature by 1 unit on Celsius scale, Kelvin scale also it will be reduced by what? 1 unit. Means, say for example, from 100 degrees Celsius, we reduce by 1 unit, means it becomes what? 99. So the Kelvin scale temperature will be what? From 373 Kelvin, it will become what? 372. So the change in temperature will be same on both Celsius scale as well as Kelvin scale. Means if you reduce the temperature by 62 on Celsius scale, means Kelvin scale also what is the reduction? 62. So look at it. The efficiency is doubling, means 2 times of 1 by 6, that is 1 by 3. That is the new efficiency. 1 by 3 is equal to what? 1 minus, here the sink temperature reduced, it is what? T2 minus 62. Source is as it is, T1, no change in the source temperature. Now look at this. What do we have? 1 by 3 is equal to, we'll take an LCM, T1 minus T2 plus 62. Cross multiply, what we'll get? T1 on the LHS is equal to what? 3 T1 minus 3 T2 plus 3 into 62, that is 186. So from here, if you look at, there is already a relation that we have. What is it? 5 T1 is equal to 6 T2. Anyway, we'll try to use that, but let us just look at it here. No, so we'll bring this T1 to the right side. It will become minus T1. So what we have? 0 will be remaining on the LHS. So I'll just write it at the top. 0 will be remaining on the LHS. 0 is equal to what? LHS, it will be what? 0. RHS, what is it? 3 T1 minus T1 minus 3 T2 plus 186. This is what? 2 T1 minus 3 T2 plus 186 is equal to 0. So if you look at the first equation, right? What is this? Is the equation 1? No. 6 T2 is equal to 5 T1, means from here, if you divide both sides by 2, then what we'll get? 2.5 T1 is equal to 3 T2. Divide both sides by 2, means in place of 3 T2, what we can substitute? 2.5 T1 plus 186. 0 is equal to, this is what? Minus 0.5 T1 plus 186. We'll just bring it to the left hand side. What do you have? I'll erase the part. So the left hand side, if we bring it, means it will become what? Plus. It will be becoming what? Plus. So on the LHS side, what we are going to have? We will be having 0.5 into T1, correct? We'll have what? So this problem of course requires some amount of lengthy calculation. So what we'll have in the left hand side, 0.5 into T1 is equal to what? 186. 0.5 means what? Half, right? So half T1 is equal to 186, means T1 is equal to what? 186 into 2, that is what? 6 2s are 12, 7, then 372. So this is the temperature that will come on the Kelvin scale, mind it. So Kelvin scale 372 means if you look at the options, right, they are giving the options in terms of Celsius. So T1 in terms of Celsius will be what? 372 minus 273. That is the conversion, right? From Kelvin, how do you get the Celsius scale temperature? We have to subtract 273. That is what? 99. So what is the answer for this? Option C is the answer. So once we get that idea that okay, this is a problem related to the Carnot's efficiency factor, right? We'll be able to easily go and get the answer. The only thing is it involves little bit of calculation. We'll get like two equations. We have to merge them to find out what is the sink temperature, and as well as we can find source temperature. In this case, what is asked? We are asked to find what is the source temperature. Here we can even find what is the original sink temperature also, but that is not asked in this question. Okay, so in some other question they can be asking both. They can be asking what? They can even ask us what is the original sink temperature, like that they can ask. Here they only ask source temperature, means we got the value. What is it? 99 degrees Celsius. We'll move on to the next question. This is another question based on the Carnot's engine. A Carnot engine whose sink, this is our T2, the usual notation that we use in the Carnot's or any heat engine for that matter. Carnot's engine whose sink is at 300 Kelvin has an efficiency of 40%. They are giving us the percentage efficiency. Means if you talk about the efficiency factor, means what? 40 by 100, that will be 0.4. That is what will be the efficiency factor. By how much should the temperature of the source be increased? Means, you know, they are asking by how much we should increase the temperature of the source so as to increase its efficiency by 50% of the original efficiency. Means we have to increase the efficiency by what? 50% of the original efficiency. So you look at it, no, what is the original efficiency factor? That is here 0.4. What do you mean by 50% of that? 50% of that means what you have to do? 0.4 into 50 by 100, that is what? 0.2. So they are saying the efficiency has to be increased by 50% of the original efficiency, means the final efficiency factor should be equal to what? 0.4 plus 0.2, that should be 0.6. Okay, so here also we'll have what? Equations. What are the equations? Initially, what is the efficiency factor? 0.4 means 1 minus T2 by T1 is equal to what? 0.4. That means when we rearrange, right, 1 minus 0.4 is equal to T2 by T1. That means 0.6 is equal to T2 by T1. If you want to get it in terms of the integers, we can do what? 0.6 can be written as what? 3 by 5. 0.6 can be written as what? 3 by 5. So 3 by 5 is equal to T2 by T1, which means 3 T1 is equal to 5 T2. This is our equation 1. Okay, and here what is the temperature that we have for the sink? T2 is given to us. T2 is what? 300. Means from here we can find the T1. So 3 T1 is equal to what? 5 into T2 is 300. So from here 3 ones are 300s. So what is the T1 value? 500 Kelvin. That is our original. So T1 initial, what is it? 500 Kelvin. Now in the second case, we are talking about the efficiency becoming what? The efficiency is becoming 0.6. In that case also we will find what is the final temperature of the source. We will see the difference between them and then we will know by how much it has to be increased. Okay, what we are going to do now, we will look at the second case. Second case means what? The second case efficiency is how much? 0.6, right? So 0.6 is equal to 1 minus T2 by, here we will call it as what? T1 dash, because here T2 is as it is, but T1 is changing. Now we will rearrange. So T2 by T1 dash is equal to what? 1 minus 0.6, that is 0.4. 0.4 can be written as what? 2 by 5. So T2 by T1 dash is equal to what? 2 by 5. Means we are looking for T1 dash, right? We'll bring everything to the other things to the left side. So 5 by 2, the factor will become what? 5 will come to the numerator, 2 will go to the denominator. 5 by 2 into T2 is equal to what? T1 dash. T2 is what? 300, right? So 5 by 2 into 300. What is this? 2 ones are 2 150s. 150 5s are what? 750. So that is our T1 dash. So the T1 dash, the final state is what? 750 Kelvin. They are asking by how much it should be increased. Means what? From 500 it should be increased to what? 750. So what is the increase? Increase is what? 250 Kelvin. So what are we doing in this question? We are looking at what is the original efficiency factor. Final state, how much should be the efficiency factor? They are saying efficiency factor should increase by 50%. So we got the final efficiency factor. Initial efficiency factor, when we use it, we will get T1 original or initial. If we use final efficiency factor, we will get T1 dash, the modified or the final temperature of the source. They are asking by how much it should be increased, means what? The difference. Initially 500, finally 750. What is the gap? 750 minus 500 is what? 250. Okay. So this is about this part video, and we will see in the next part.